Scikit-Learn and Xgboost are machine learning frameworks, and you can, as part of the Python ecosystem. And I'm a huge fan of these frameworks. I use them for my work, and I genuinely find them to be a joy to use. If you're experienced with Scikit-Learn and Xgboost, this talk is meant to give you some practical tips for how you can use the cloud to get your job done better. But if you're new to the frameworks, the next couple of slides will give you a quick introduction. So the first thing to understand is that Scikit-Learn and Xgboost are part of a larger Python ecosystem for data science, which is incredibly rich. From low-level libraries like NumPy and Pandas, all the way up through graphing and matplotlib and the frameworks we're talking about today. Python has a ton of frameworks to make data science easy. Python was the most preferred tool cited in Kaggle's most recent ML and data science survey. Scikit-Learn is an open source framework on Python for doing a wide variety of ML tasks. The name Scikit-Learn is derived from it being a toolkit for machine learning that's part of the scientific Python community. And I have to say, I'm personally thrilled to be here today with David. In 2007, David created Scikit-Learn as part of a Google Summer of Code project. Scikit-Learn is, by the way, often abbreviated sklearn, and I think you'll hear us use both terms interchangeably. So unlike Scikit-Learn, which supports dozens and dozens of algorithms, XGBoost supports one, but does a fantastic job with it. Basically, XGBoost stands for Extreme Gradient-Boosted Decision Trees. So gradient-boosted decision trees are ensembles of decision trees in which each subsequent tree attempts to sort of correct the mistakes made by the prior trees. And it's proven to be an incredibly effective method of doing ML. I was talking with Ben Hamner, who is the CTO of Kaggle, and he told me that XGBoost is behind almost every recent winning submission to a Kaggle competition, except for computer vision competitions. And that brings me to an important point. So neither XGBoost nor sklearn is optimized around deep learning or neural networks. And that's a key difference from TensorFlow. Now, you're at a Google conference, and you're hearing a lot about TensorFlow, so I just want to take a moment here. TensorFlow is truly remarkable, and you should definitely go and learn a lot about it. But for a class of problems, and I think for a class of problems that happens to actually be very common in businesses, I think the ROI from XGBoost and sklearn can be higher than TensorFlow. You'll get great results without a ton of effort. So we're going to focus on 3 stages of ML during today's presentation. Preprocessing is the stage in which you make data ready for training. Training is the stage in which you take labeled data, train on it so that you can predict a target variable in the future for unlabeled data. And then prediction is the stage in which you take unlabeled data and predict new values for it. And how do these frameworks play into these 3 phases? Preprocessing often requires transformations in NumPy or Pandas, but Scikit-Learn also provides its own libraries for preprocessing. You can do feature selection and feature engineering with Scikit-Learn itself. And one of the best things about Scikit-Learn is the consistency of its interface. So you can take any algorithm in Scikit-Learn and call .fit on it and get a trained model. And once you have a trained model, you can take any of them and call .predict on it and get predictions out. This interface is incredibly powerful, and I think it's what makes Scikit-Learn a ton of fun to use. XGBoost supports that same interface, which is really cool. So if you built your sort of pipeline to use Scikit-Learn, you can often switch XGBoost into it pretty seamlessly. And one of the things you'll see today is that we're going to do some demos. The demos all use Scikit-Learn and Scikit-Learn pipelines, but you can easily switch XGBoost into them without much effort. So let me talk about our agenda for the rest of the talk. We're going to divide it into 3 sections based on the Google Cloud services that are demonstrated. And during these 3 demonstrations, we're going to refer back to those stages of ML that I just showed you. So in the first case, what we're going to show you is how you can use Google's building blocks APIs to pre-process unstructured data so that you can use it in XGBoost and Scikit-Learn. And in the second phase, we're going to talk about Compute Engine and how it can help you do ad hoc data analysis at scale very easily and without the pain and the difficulty of distribution. I like to refer to that part of the talk as the part where we make distributed computing uncool again. And then we're going to finish by tackling the topic of productionization, in which we think about how to integrate ML into your production service in a highly reliable way. And that's the part where we're going to talk about Google Cloud ML Engine. All right, so let's dive in. So Google's machine learning building blocks. These are pre-trained models that you can call into, and they're accessible by API. You basically can use these models to process unstructured data and utilize Google's deep learning expertise without having to train your own model. Building blocks exist for natural language, speech, translation, video, vision, and more coming at this conference. And increasingly, you can customize these API endpoints to your business's needs with AutoML. So they're becoming significantly more powerful and flexible. I've talked a little bit about structured and unstructured data, and I just want to quickly define those concepts. Structured data, essentially big tables of rows and columns of strings and numbers, is in the grand scheme of things relatively straightforward to pre-process. You can do it with expressions. It's not that dissimilar from spreadsheet operations. And if you need to do it at scale beyond what fits in memory, you can use things like BigQuery or Spark or Beam or Dataflow to do that. But unstructured data like images, long paragraphs of text, or video is more tricky to pre-process, more tricky to handle in ML. And it's really where deep learning and where neural networks shine. And there's a lot of talks here about those topics. But an alternate path, if you don't want to write your own neural network, is to utilize Google's building blocks APIs. So just as an example, if you have a bunch of images in your business, you could train an algorithm on them by extracting the objects within the images and then use that as structured data in a traditional ML approach, like Scikit-Learn or XGBoost. Or, here's another interesting use case. It came to us from a customer engineer in Japan whose name is Hayato Yoshikawa. I'm also going to take this moment to just say that in this talk, I will occasionally have to mention Japanese and French names, and I'm terrible at pronunciation, and I deeply apologize for butchering these languages. Hayato showed that it's possible to use Google's natural language API to solve a tricky problem with Japanese text. So most NLP, most natural language processing, starts with extracting the words that are in a sentence or a paragraph of text. And in English, this is easy. You just split the text on the spaces. But in East Asian languages, it can be more difficult because there aren't spaces between the words. So what Hayato showed is that you can pass the sentences to Google's NL API and extract the tokens out. The results he saw were much better than you get from Python libraries. And with the tokenized text in hand, you can pass it to Google, to Scikit-Learn's text preprocessor and go on your way. So let's see this in action. I'm going to switch over to my demo box. Take me a second. Awesome. OK. So the demos today are in Jupyter Notebooks. And if you're not familiar with Jupyter Notebooks, I really suggest you take a look at them. They're a ton of fun to use. They're sort of like an advanced version of a REPL, a read, eval, print loop, where you can execute code, mix and match it, and sort of intermix documentation with code. So in this demo, what we're going to do is we're going to pre-process headlines from Hacker News. It's an open data set on BigQuery. And we're going to try to figure out whether the headline is from TechCrunch or from the New York Times by identifying the most salient words in the headline. Let me talk quickly about the dependencies here. Basic stuff like pandas and NumPy. And then, oops, excuse me, I'm on my second demo. All right. Basic stuff like pandas and not NumPy, as well as text preprocessors from Scikit-Learn, and 2 Google client libraries. So the first here reads data from BigQuery, and then the second here communicates with the natural language API. So let's run this line of code here. And you know what? I'm going to restart my kernel so that I just clear all the output. I don't want to spoil the surprise. All right, let's start this again. Perfect. So we've imported our dependencies, and now we're going to query the data from BigQuery. This is something I really love about notebooks. You can mix and match actually different forms of code. So in this notebook, for instance, we're mixing Python code with these BigQuery magics. Magics are add-ons you can install into notebook environments to do particular things. In this case, the BigQuery magic allows us to write a query here, and with just very, very simple amount of code, read it into a pandas data frame. So here's that data frame, or a preview of it. The source here is the target variable, and the sentence, the headline, is here on the right. So let's do a first attempt to tokenize with Scikit-Learn, and we'll see the problem. So the problem here that you see is that the English text is successfully split into its constituent words, but the Japanese text is left completely alone, which is because Scikit-Learn is just naively splitting on the spaces. So now let's use Google's natural language API. We create a language service client from the Google client library, and for each piece of Japanese text, we pass it to this tokenize function. What the tokenize function does is it calls the analyze syntax method on that client, takes the return value from that, and extracts the tokens. The tokens are joined together with spaces and inserted back into a new column in the data frame called tokenized text. And now, if we run this last cell in the notebook, we'll just show that we've solved the problem. We've run the exact same set of code, but this time the Japanese text is successfully split into words. It's a very sort of like simple example, but I think what's cool about it is it hides a ton of complexity. So let's go, here we go. Oh, by the way, the links to all the code are going to be available on the last slide of the deck. So Google's high-level machine learning APIs can be useful in pre-processing data, but how about infrastructure as a service? Are we really going to talk about virtual machines in this talk about machine learning? And the answer is a resounding yes. So what kind of scaling challenges do users of Scikit-Learn and Xgboost typically run into? Well, scaling can require more memory if your data set is very large. It can require more CPU, or GPU, or TPU, if the best ML algorithm for the task is computationally intense. And it can require more processes or threads if you have a big hyperparameter space to explore. And so when you need to scale, you typically think about parallelizing your work. So let me talk about different ways you can parallelize your work. Hyperparameter tuning is embarrassingly parallel. Embarrassingly parallel because it's so easy to parallelize. The only information that needs to be shared from the workers back up to the scheduler is just the final results, and then the scheduler just picks the best one. Both Scikit-Learn and XGBoost allow HP tuning to be parallelized. Also, there are ensemble methods of ML like random forests that can be parallelized. And preprocessing can be parallelized. So you can switch from pandas to Dask. Dask implements the pandas data frame API, but does so in a parallelizable way. I mean, it's super cool. And I think when many people think about parallelization, they immediately think about distribution across multiple nodes. And I think that's because our industry has made a ton of amazing progress in the last few years through distributed computing. However, oftentimes you can actually get a lot done with a single node, and it can be really easy to do. Using large compute instances to do your work is becoming increasingly more and more of a reality as costs come down and the capacity of nodes increases dramatically. So here to tell you more about this is David. David Cornepo leads the ML team at Cogent Labs, which is a business in Japan that specializes in applying deep learning to B2B markets. And as I mentioned, in 2007, he created Scikit-Learn. Thanks.
Okay. Thank you. Can you hear me? Okay. It's good for the sound. You can all hear me? Okay. So thank you, Steve. Thank you for having me. I'm excited to be here. First time at Google Next. So as Steve mentioned, I've been working for almost 1 year now at Kojan Labs. It's a startup in Japan, Tokyo, where we do deep learning. And so we try to apply deep learning to problems that were difficult to solve before. So for example, we have a product called Tegaki, which is Japanese handwriting recognition using deep learning. We have a product called Kaidoku for document understanding. And we have also like a system to do time series production. But today, actually, I'm not here to talk about deep learning, but I'm here to talk about a lot of the work that happened before, like when you need to deal with the data. Because Steve already mentioned, when you do machine learning, you need to actually spend quite a bit of time on the pre-processing. So it's kind of the unsexy part of data science and machine learning. Realistically speaking, when you work on product, that's most of what you spend your time on, more than on the models themselves. And this part is actually not that different, whether using machine learning, like traditional machine learning, like Scikit-Learn, or whether you're using deep learning through frameworks like TensorFlow. So I want to talk a bit more about that part, actually. So, like the example I will use to illustrate a bit my points is using one of the projects I've been working on at Kojan Labs for the financial time series forecasting. So we did this project in coordination with one of the biggest brokerage company in Japan. And we used basically deep learning to do time series prediction for real-time volume prediction on the Tokyo Stock Exchange. And the product has been live since last month, actually. But yeah, like to use a deep learning algorithm, you need data. And it's kind of a truism today. Like, the more data you have, the better it is. And so you have this famous paper from like 10 years ago by Alan Havley and Peter Novick about like the unreasonable effectiveness of data. So Peter Novick is the head of research at Google, actually. Another thing he mentioned early on when he was at Google is, at Google we don't have better algorithm, but we have better data, we have more data. And like he said, like some things that really, he knew that already intuitively before, but like some things that really kind of, stayed with him, like when he was at Google, was how like even simple algorithm can work so well when you have a lot of data. So this whole argument about the unreasonable effectiveness of data and how you can generally improve your product, not by changing the model, but just by using more data. So with this whole thing about, it's almost a fad at that point about large data, big data, and the more data you have and the better it is, right? You have more and more data, internet, blah, blah, blah. What can you do? Like, do you need to do like distributed computing? Do you need to always use Hadoop? But only have like 2 engineers? How I can do this, right? So there's this, at that point it's almost a fad, but it's still real thing for some companies where you have large data to use for your algorithm. And the problem is when you have a lot of software engineers, they kind of like using tools for distributed computing because it's fun and you have a lot to do, right? So you have all these great technologies like Hadoop, Spark, Kafka, Beam. Some of them will be mentioned or have been mentioned already in this conference. And so yeah, as I said, like engineers, they love working with distributed data system because it's fun. But, like, is really large data really eating the world, so to speak? So this paper I really like. It's a bit old now, but I think the lessons are still relevant today. Like nobody ever got fired for using Hadoop. And so, like, again, the numbers are a bit old because they're from 2012, but I've noticed the same thing, in my previous job and even currently. Like, so in this paper in 2012, they look at what was the median size of a job in Hadoop. And at Microsoft and Yahoo, the median size was below 14 gigabytes. And at Facebook, 90% of the Hadoop jobs they were using at the time were for a job input size of below 100 gigabytes. And so there's this joke where like a lot of people, like they say, oh, I have a lot of data, I have gigabyte of data, so I will use Hadoop, right? And so there's this famous blogger and like conference speaker, Gary Burnett, where he had this joke like, I have these new consulting services where, you bring me your big data problem, and I will tell you, well, your data actually is small enough to fit in RAM, you pay me $10,000, and then you don't have to spend $500,000 on your infrastructure. And it sounds like, almost trivial, right? Like, you're like, I will never make that mistake, right? Of course, you have like a small data set, I will not use Hadoop. But there's something I keep saying. Like, at the beginning of this year at PyData in London, I was talking to this guy working for a hedge fund, and he said, like, when he joined, like, there was this team of 15 people doing Scala distributed system for data sets that was 40 gigabytes. he fired all of them and built a system that was a bit better designed. So that's the one big lesson I want you to remember. You know, maybe some people don't make that mistake. Maybe when you have a bit less experience, it's easier to do this mistake, but don't over-architect. And the thing is, when you do like machine learning, like the typical data size for ad hoc analysis is often not that big. Sure, you have more and more data. And of course, if you're Google, you have a large data set. If you like other companies have a very large data set. But most companies, they don't have that data, that big of a data. And the thing that is interesting as well, like maybe you're storing more and more data, but the data you need to look at when you look for a new problem to solve, or maybe to improve an existing algorithm, you don't need to use all the data at once, right? Like especially at the beginning, when you do ad hoc analysis, you're not sure exactly what you're looking for, you want to understand a bit better your data, you can use a subset of this data to do the analysis. So the size of the data for analysis is not the same size as the data you need for storing. And it's very easy to underestimate the work, the engineering work you need to deal with like effective data architecture. Like, you know, for people who've used Hadoop, they know, like, you know, you don't set up Hadoop in 1 hour and then you're done and you're using it, right? You need people to take care of it, like master nodes fail, you know, like some of the hardware fail, and you need to take, that's a lot of work to deal with it. And especially when you're a small company, I think it's easy to underestimate the loss of what I call data agility. That is the ability to be able to not scale the amount of data, to scale the number of experiments you can do with the data. Like having data this small enough, you can easily visualize it, you can understand it. It's really important for some class of problems as well. And again, you know, like most of the work around machine learning when you work on product is not on the model itself, but everything around. So if you optimize the part where you need to have like ad hoc analysis, when you need to do an ad hoc analysis, if you optimize that part to be like simple, where like all your data scientists can work on like a setup where they don't have to fight the system to get the data, you can get actually a lot back because you can be faster and you can develop new model faster, understand your data faster, or plot the data faster. Okay, so what's the link of this observation with like Google Cloud? So again, data are getting bigger, you know. I mentioned before, don't try to over-architect too much your data architecture. But something that is interesting when you think about cloud services, and GCP in particular, is you can get like really, really large VM now. Like recently, GCP announced that you can have VM with 4 terabytes of memory. That's a lot of data you can keep in memory on one machine. And when you look at the trend of like what is the typical data size that people use in data science, actually you see it's kind of plateauing. Like, so it's just one data sample, but you have this, so KD Nugget is a famous data science website, and every year, they do a survey to ask people, you know, what is a typical data size you're handling, etc. And actually you see that for the last few years, like the median data size of the data that people look at is plateauing at a few hundred gigabytes. And 5 years ago, a few hundred gigabytes, yeah, maybe you had to use Hadoop, or at least, you know, you need to think a bit. You couldn't do it trivially. But today, a few hundred of gigabytes, if I have to deal with this today, I know what I will do. If I can put the data on the cloud, I will just put them on a large VM, where I can load everything in RAM, and then everything becomes much easier for me, and I don't have to overthink too much about the engineering part. It's not just about the RAM. Okay, there's the CPU. It's also kind of obvious. But also, like, you know, at least on GCP, you have also like fast local I/O available, right? You can create VMs that have NVMe SSD, where you have more than 1 gigabyte per second, like throughput when reading from disk. So all of this together means you can have like very powerful machine where you can actually get a lot done without going too early to distribution. The advantages are fairly obvious, right? If you are scientists who are maybe not so strong on the software engineering side, they can focus on their domain expertise. They don't need to spend time learning about Hadoop, about Pig, Hive, whatever. And they keep all the tools, all the interactivity of the tools that people like to use in data science, especially in Python, and some of the tools that Steve mentioned before. So you keep the interactivity on single machine, and you keep, like, using the notebook is easy, using Matplotlib, Seaborn, Pandas, all of that keeps stays easy. So concretely, if you look at, I was mentioning before this project we did with investment bank in Japan. So we have a fairly typical problem. Like we use deep learning after, but it doesn't matter so much from what I'm talking about here. So we use a market data. So we have tick data. So tick data, for people not familiar, is just like the price of each stocks at each moment is coming from the market. So concretely, we have like between 1 and 200 gigabytes of CSV files. It's already semi-aggregated. We have like 50 million points per month. So we had a bit more than 2 years. So we have a few more than 1 billion data points. And some of the analysis we had to do was pretty easy to parallelize if you want. Like some pre-processing, it's each row independently, so you could parallelize that fairly easily. Some things are a bit less easy to parallelize, like resampling. You had this thing called open bin detection. It's boring, but basically it's kind of recursive, so it's more difficult to parallelize. And at the beginning, the pre-processing we had was quite resource hungry. Like you needed more than 100 gigabytes of RAM just to deal with one of the CSV files we had. So to make it a bit more concrete, I just show a bit how it looks like. So you don't need to really understand the numbers, but like when you use market data, the problem is each market data provider has different conventions. So you need to convert between different market data providers to a common format. So kind of boring, but again fairly typical things like removing some characters in the symbol, all of these kind of things. And we need to do that for quite a few data points, so several billions. And so we need to speed this up. And so you may wonder, why do you need to speed this up, right? Like pre-processing, you only need to do it once. You can save that into a data frame, or maybe you can save that into Parquet file, which is a more modern serialization format that can be serialized quickly from and to disk from Pandas data frame. But the problem is at the beginning, we were not sure exactly which kind of pre-processing we had to do. Because again, those market data are pretty complicated, and different banks actually deal with them differently and have different conventions. So you had to go back and forth with the customer quite a few times. And so the speed of processing was actually kind of important, because if it takes 1 day versus 1 week, well, it kind of makes a difference when you need to talk to the customer back and forth. And so just by using larger VM on Google Cloud, nothing fancy, pandas, bash scripting, a bit of a parallel option to Xargs, you actually could get quite a lot done. And having the big VM allows us to iterate quickly, especially in exploratory phases. And having big VMs really allows us also to convert the CSV very quickly to some other file format that are more efficient on the disk and on memory. So really the takeaway here is, there was this fashion of, always scale horizontally because scaling up doesn't scale. Well, actually, for a lot of things, scaling up actually does scale, right? Especially with the cloud now, it's quite easy to get really large VM. And as long as you do that, for ad hoc analysis, I actually think it works pretty well. You can keep iteration quickly for doing ad hoc analysis. I think VM actually are getting bigger more quickly than data are getting bigger. And at the same time, you have tools that become more memory efficient. So for example, for pandas, the rule of thumb for Wes McKinney, the creator of pandas, is if you need to deal with a data set of size X, generally the rule of thumb is you need 5x to 10x of RAM to deal with this comfortably into pandas. But now with tools like Arrow, this factor becomes smaller, so it's actually more memory efficient. So for a given amount of RAM, you actually can get more done or get larger data. And some of those lessons, they are not specific to ad hoc analysis, just pre-processing or ad hoc analysis, but actually you can apply this in later phases as well of your project. So one of the ways I like using this kind of technologies is for testing and continuous integration. Doing continuous integration for machine learning models is pretty difficult, right? How do you write unit tests for machine learning models? How do you write, it's not as mature as for standard software engineering. And sometimes one of the issues is that it takes a lot of time to just test even simple things in your models, especially when you do deep learning. Well, here again, if you can launch on demand just for half an hour, very large VM with a lot of cores, you can actually get away with simple solution, and you don't need to, again, over-architect too early. So it's not all the lessons I'm giving here. Well, they are simple tricks, and maybe it's trivial for most of you, but you can use them not just for ad hoc analysis, but also for testing integration. Okay, I will give back to Steve.
Perfect. Thanks so much. You can take that. Thanks, David. Perfect. So as you think about scaling up your training on single nodes on Compute Engine, I want to call your attention to two resources that I think can be really helpful from Google. So the first is called Compute Engine Burst Training, and there's a link there. It'll also be at the end of the deck. It's all on GitHub. It's just a pattern for doing your work. And basically, it's a set of scripts that allow you to automatically provision a machine, kick off training, export the results of training to cloud storage, and shut down the machine. That's all done for you so that you can basically get your code correct on a sample of your data on your local machine, and then when you want to train on your full data set, you do that on the cloud, but you do it in a way that minimizes your costs. So you're able to just provision that very 4 terabyte machine for just the period that you need. And the other became available just about 2 weeks ago on Cloud Launcher. It's called the Deep Learning VM image, and while it says deep learning, I think it's really helpful for XGBoost and sklearn as well. It automatically installs pandas and NumPy and other common dependencies. It automatically starts up Jupyter, provisions an SSH tunnel, and gives you a little command to basically browse to that to Jupyter from your local machine. Again, none of this is rocket science, but it can just make your life a little bit easier. Okay, so now it's time for our last section. CloudML Engine. This is all about productionization and taking your code and moving it into a production service, which means that it's highly available, that you have a repeatable process for deploying and updating, and that it responds to real-time changes in demand. And so if your service relies on prediction for real customer experiences, or if you regularly retrain your model on new data as it comes in, CloudML Engine can be a real help. And at this conference, we have announced that Scikit-Learn and Xgboost are both supported for training and prediction, and both services are generally available. So first, let's talk about prediction. It's simple. From XGBoost or Scikit-Learn, just export the model to a file, upload it to CloudML Engine. You'll have a REST endpoint that you can use to handle predictions. CloudML Engine runs on Google infrastructure, so Google SREs are holding the pager. And as you'll see in this demo I'm about to show you, it can help you avoid training serving skew. So training serving skew happens when you process data differently in training and in prediction, and it can lead your predictions to just not live up to the expectations set during training. And the solution to avoid training serving skew, or one aspect of avoiding it, is to make sure that you share your pre-processing code between training and prediction. And CloudML Engine, together with Scikit-Learn pipelines, can help you do exactly that. So let's take a look at a demo. All right, so again, this demo is in a Jupyter notebook, and this time we're going to predict the weight of babies. Again, it's a data set on BigQuery public data. Predict the weight of babies given basic information that we might have available when an expectant mother walks into a clinic. We know the age of the mother and the father, the gender of the baby, and the length of the pregnancy. In this demo, we've got a couple of interesting dependencies from Scikit-Learn that I just want to show you. The first is a dictionary vectorizer. This is what we use to one-hot encode. So it's a really slick piece of Scikit-Learn that just takes categorical data and automatically one-hot encodes it. Some of you may call that dummy encoding, not one-hot encoding. But it basically turns categoricals into numbers so that they're easily understandable by an ML algorithm. We're training using a random forest, but it could be any model. We're joining together those two pieces together in a Scikit-Learn pipeline. We've got utility functions for splitting our training and test set, and joblib for exporting the model. We're going to use the Discovery API from the Google API client to issue predictions, basically just build up a REST request. And we are going to also use BigQuery to read the data. So let's run this. And it's great. Again, we load our data from BigQuery. And here's the data. The weight here is the leftmost column. That's the target variable. The rest of the columns are the features we're using to predict it. So let's do some basic data processing, separating out our labels from our features. making sure that our categorical data are of type string so that the dictionary vectorizer will correctly handle them, and then splitting our training and test set, and constructing the pipeline. At this point, we have a pipeline ready, but we actually haven't done anything with it yet. This next step, and again, this is calling the .fit method, fits the pipeline to the data. And this output shows us that the pipeline is correctly fit. So what that did is it actually ran both steps in succession. First, it ran the dictionary vectorizer, then it trained the model. And then on the local machine, we can then call .predict on the pipeline and get our predictions. Now, all of this has been done locally, which is all well and good until you want to run it as part of a production service. So now, let's do that. So we're going to use joblib to dump out the data to the local file system and then copy it up to cloud storage. There's another cool thing about notebooks here is that we're mixing together a magic that sets an environment variable with a call to the shell, which calls gsutil and copies up the data. So the data's up there now, and now let's create a model. You can see I've practiced this demo 9 times. All right, we're going to create the model, and the model is just a container for us to then put versions of the model, and those are which will actually serve predictions. So the meat of the work is this command, and I'm going to run it and talk you through it. It's a call to gcloud, and we're creating a version of the model asynchronously. That just means the notebook returns and continues execution while waiting for the model to finish. We're passing it the model and version name we just created. We're specifying that the framework is Scikit-Learn. So the other 2 framework options are TensorFlow and XGBoost. The runtime version of 1.8 is a CloudML engine runtime version that specifies a version of Scikit-Learn and a version of other dependencies that are available to us. We point to that file that we just uploaded to cloud storage. And we also specify that at all points in time, there should at least be 1 node servicing traffic. I may have mentioned earlier, but one of the cool things about CloudML Engine is it scales up or scales to 0. And if you have 0 nodes servicing traffic, you pay nothing, which is really nice. But your business may require you to always have 1 node servicing data, because there is a small latency cost of tens of seconds if you're the first request to sort of provision a model. If you want to avoid that, you can do this. OK, now let us see if the model is ready. It is not ready yet. Let's give it 1 more second, and then I'll call the one before that. All right, it's ready. So that shows you about how long it takes for the model to deploy. And this last cell in the notebook is Python code. It could be any language you want. This is just an HTTP request to a REST endpoint. We use the Discovery API to make it easy to build up the request, and then we issue it, passing the test instances in the payload. And we print the predictions out to the notebook. And if these numbers look familiar, 6.4472.21, it's because those are the same numbers that we saw up here, which is just an indication that shows that we've basically taken the same logic that was running locally, and we've moved it up to the cloud. Cool. Awesome. But prediction is usually only part of a larger end-to-end pipeline that can involve retraining as well. So here to tell you a little bit about how that can work is Laurent Candelier. Laurent is a senior data scientist at Ocado.
Thank you, Steve.
You're welcome.
Thank you, Steve. Let me start with a quick context. Ocado has been an online retailer in UK since 15 years, and it has known great success. Thousands of orders are placed every day through our website or application. Then products are picked up by hundreds of robots in our huge automated warehouses, and happy drivers come to your homes to deliver your goods whenever you want. And with time, Ocado has also become more than just a retailer. It has become a tech company robust enough to sell its technology to others, from the website and the app to the full system of delivery, using the full automated warehouses and more big data and AI. Some of the biggest retailers in the world join our adventure, like Morrisons in UK, Bonpreu in Spain, Casino in France, Sobeys in Canada, ICA in Sweden, and Kroger here in the United States. So I have 5 minutes to go to the point, so let me jump to an example where the experience of Ocado in big data and AI can help other retailers. Fraud detection is a classical problem that we face in online retail, orders being delivered and never paid for. How can we face that? With machine learning, for example. Features can be derived from orders and passed along with the known class of failed payment or not to a machine learning algorithm that will learn a model that will then be able to predict if a new incoming order will probably be associated with failed payment or not. Type of rules that such an ML models can learn is if you pass more than 3 orders in the future for more than £500 each and you let us less than 24 hours to do the delivery, well, your orders are suspicious. And remember one important thing, we are speaking about big data here with all the retailers in the world that joined our adventure. So the big question is how to embrace the challenge of quickly building scalable machine learning solutions ready for production. As quickly as I jump to the problem, let me jump to the solution. It's called Google Cloud Platform, a great environment to run machine learning on the cloud. You can start with your data lying in Google BigQuery and run some standard SQL to join your data coming from different resources and run some initial computation of features. You can then go to Google Dataflow to run some Apache Beam to run some more complex data processing like data normalization, for example, or data transfer to other resources like data store that can be used as a fast data access solution to expose some of the pre-computed feature you will need at serving time. You can also use Google Cloud Storage to store all your data sets as files that will then be read by Google Cloud ML Engine to learn a model and expose it as a REST endpoint, and thus be ready to serve prediction in real time. And here is the important thing. When we run the analysis of comparing machine learning algorithms to face this problem, we found that XGBoost, like in many cases, were the algorithm reaching the best predictive performances. But we chose to go to TensorFlow neural network instead because it was embedded in Google Cloud ML Engine, and thus we were allowed to train and predict in the cloud, and thus we were offering a solution to quickly go to production and to be scalable. We would also have liked to use, for example, decision trees, for example, in Scikit-Learn, to be able to understand the output of the models and the prediction. But again, we chose to go to TensorFlow neural network. And basically, with the work of Steve's team, this conscious decision is not needed anymore. We can take the best of all machine learning algorithms using XGBoost and Scikit-Learn on the cloud, deploy easily, train and predict on the cloud. And so we can now have better predictive performance with XGBoost. And the explanation for fraud detection can be important because it can be interesting if you provide the information to a human to explain that you think that this order is fraudulent because of the basket content or because of the past behavior of the customer or because of the payment method that is used. But then if you want to really take decision automatically for legal reasons, you need to be able to explain your prediction. So this explainability for us is important. So yeah, basically big data, machine learning made easy on the cloud. What's next, Steve?
Great. Thanks, Laurent. Actually. Awesome. I'm always happy to take credit for things, but I also want to just note that I saw Marielle and Robbie walk into the room a few minutes ago, and I did work on it, but they were really the folks who did most of the work. So thank you. So let's sum up by dispelling a couple of myths. I think you'll sometimes hear that you need neural networks in order to do machine learning these days, and I don't think that's true. I think hopefully we've shown you today that Scikit-Learn and Xgboost can be really helpful in solving a bunch of business problems with ML. And if you do have unstructured data like images or audio files and you want to make sense out of them, another option, instead of building your own neural network, or certainly something to consider, is to process them through our building blocks APIs and then take the structure out of that and then use XGBoost or Scikit-Learn. People may tell you that you need to leave the Python ecosystem to scale. I also don't think this is true. I think using some of the techniques that we showed you today, you can scale up on single machines and get a ton of amazing work done without having to sort of go to a distributed framework. And people may tell you that the only way to productionize is to embrace containerization. And certainly, containerization has its place, and there's lots of places where it's very, very appropriate. But I think for many folks, the ease of use of a managed service like CloudML Engine can be very compelling.